Hello again. In this lecture, we'll examine how to create histograms in NumPy. However, since NumPy contains no plotting functions, we're going to get some help from additional packages. Before we spoil all the fun, let's get coding. To begin, let's redefine the same old 2D array called matrix A. Once again, we'll stick to using the same values of the matrix, so we can just execute this cell. Done. So a histogram is a way to examine a dataset by dissecting its density. What is a density? Well, it's how populated a given area is. In statistical terms, it refers to how many values from a dataset fall within some predetermined range. In the case of a histogram, we're measuring how many values of the original dataset fall within each interval. To construct a histogram, we can take the range from the minimum to the maximum of an array and slice it into consecutive equally sized chunks called bins. Then we count how many elements of the dataset fall into each bin to help us understand how spread out the values are. To fully comprehend the results of the histogram, we should first display a sorted version of the flattened array. That way, it'd be easier to keep track of which values fall within each bin. Of course, we can easily do that by calling the sort function, passing our matrix A as an argument, and setting axis equal to none. Now that we have the sorted array on display, let's call the histogram function and plug in the same variable. We type np.histogram and add matrix A within the parentheses. The output is a tuple containing two arrays, one full of integers and another one full of floats. The first array represents the number of times a value falls within each bin, while the second array depicts the edge of each bin. What is an edge of a bin? Well, since the bins of a histogram are conjoined, most of the time an edge is simply the ending point of one bin and the starting point of the next. After we've clarified this, you can observe the output to notice that there are 10 entries in the first array, but 11 in the second one. That is because we begin with the starting point of the first bin and end with the ending point of the last bin. Hence, the number of bin edges is always one greater than the number of bins. This is also why we said earlier that most rather than all edges perform double duty. Great! Now that we know what the different parts of the output represent, let's try to read the result. The first value on the upper row suggests there are elements in the first bin. The first two values of the second row imply that the first bin ranges from 0 to 0.9. Since matrix A consists of only integers, this means 0 appears 3 times in the dataset. Of course, we can confirm that by looking at the sorted flattened array we displayed in the last cell. Then, similarly, we see that there are two values between 0.9 and 1.8, so the set value also contains two ones. Once again, we can double-check that by examining the sorted array. We can continue examining the output values one by one, but you already get the gist of it. Before we start examining the arguments of the function, we want to point out that since the output of the function is a tuple, we can use indexing to extract different elements. For example, if we're solely interested in the density of each bin, we can add bracket 0 bracket after the function, and it will return only the first array. Similarly, if we only care about the bin edges, we can switch the 0 to a 1 and get our desired result. After this quick reminder, we can focus on the bins for a minute. For starters, bins are closed open intervals. Simply put, if a value equals the lower edge of a bin, it counts towards the bin. But if it equals the upper edge, it doesn't. Of course, the obvious exception is the last bin, which uses the maximum of the dataset as its upper limit. So it needs to include it as well. So, the default number of bins for the function is 10. However, nothing suggests this is the optimal choice for every dataset. Hence, we can change the designated number of bins in the histogram by passing a value to the bin's argument. Let's set it to 4 and see how the output changes. We still have two arrays, but now the first one contains 4 values while the second one holds 5. We already discussed why they differ in size, so let's focus on the values inside these arrays. Since there are only 4 bins, the edges are now further away from one another. Values are now 2.25 apart, meaning each bin covers a larger part of the range between the minimum and maximum values of the set. Usually, this leads to an increase in the density of each bin, since it metaphorically covers more ground. Let's see if that's the case. If we look at the first array, we'll see just that. There are 6 values in the first bin, 4 in the second, 3 in the third, and 2 in the last. Thus, the array contains 6 values between 0 and 2.25, another 4 between 2.25 and 4.5, and another 3 and 2 from 4.5 to 6.75 and 6.75 to 9, respectively. Thus, now that we have fewer bins, the average number of elements in each one has increased. All right. The next argument we want to examine is range. Setting a value for this parameter will mean that we will be defining a fixed interval, and by doing so, we can have a very easy way to ignore outliers. For example, let's set the range from 1 to 7 and comment on the results. As expected, the density array still contains 4 values. However, their sum is now 10 instead of 15. Therefore, by setting the range from 1 to 7, we're excluding 5 values from the dataset. If we look towards the sorted array above, we'll see that these 5 values are the 3 zeros at the start and the 8 and 9 at the end. However, we need to be careful when we use a fixed range because it implies a maximum and minimum value which are incorporated for the bins. To elaborate, even though the highest value in the array is now 6, it's not the upper edge of the last bin. Instead, we're using 7, which is the range we manually set. The same applies to the minimum value. You can observe that the value of 1, which is the lower bound of our range, can be encountered within the array. Nevertheless, it remains within our output. All right. We said that NumPy holds no plotting capabilities, so to get a visual representation of the histogram, we'll need to import matplotlib.pyplot as PLT. Then we need to call the hist method and define 2 values. The first one is the dataset, which will need to be a flattened version of matrix A. The second one is bins. Since the second element of the histogram output contained all the starting and ending points of each bin, we can set the bin's argument equal to it. Then we need to add a PLT show and run the cell. Fantastic! We can use matplotlib to set a title, label the axes, or change the size of this histogram. But we'll learn how to do all that in the data visualization part of the course. Before we move on from histograms, it's important to understand they can be very useful in higher dimensions as well. In the next lecture, we'll examine multidimensional histograms and what they tell us. Thanks for watching!